Well, hello everyone. I don't know if you can hear me properly, but it's good to be back. This is my second, kind of like my third. I had an unsuccessful second live stream. That's gone and disappeared into the deep darkness of history, so to say. Um, but yeah, I thought to like continue. I did like my experience of the last live stream I did, trying to solve through and implement the research paper on TensorTonic. I know it was not um, the easiest walkthrough just because I've been so out of practice and mostly because of my ignorance in some sense. But I liked it enough to like stick around and thought like, okay, let me try it again. Let me continue on this path of because I like to learn and it's a good thing to do. It is a very strange feeling to almost speak to myself or like speak to camera um, with no concurrent viewers. It seems like I'm speaking to a possible um, audience that might exist in future, or a possible audience that is me in the future, right? Like so, but that is incredibly exciting in that particular regard. Um, the it's a pretty wondrous time that we live in. That such a thing is possible, right? Okay. So with that somewhat long prelude out of the way, I thought to continue on with the "Attention is All You Need" paper. So let me share my screen. Let's see. All right. Hopefully you can see my screen. This is the "Attention is All You Need" paper on TensorTonic, which is a pretty neat website to like practice your AI concepts, implement machine learning papers, they have study plans, they have interview prep, and you can like log into. You can subscribe for a premium plan where you can have more elaborate study plans and crash course and things like that. I don't have that right now, but I like the research papers course enough to like stick around with it. For anyone that is not familiar with "Attention is All You Need" paper, this is probably one of the most fundamental paper that has defined, I guess, the LLM era that we live in right now, or like the transformer era, right? Like so, um, in this paper, which I have here is, let's see, this paper, these authors from Google Research implemented an architecture which we now know as like transformer architecture. Um, it has this attention mechanism that allows you to attend over all tokens and use that to predict the next token, so to say. And what is token? What is attention? That's something that we will learn more as we implement the paper, right? But it is an incredible thing to know that like this paper kind of kickstarted the whole LLM era that we live in right now. Right? So I've already been through tokenization and embedding. Just to give you a quick summary of what tokenization is, right? Like so, we speak and understand in the language of words, right? Like or like concepts that we can understand as words that make up sentences, or like that make up phrases, that make up sentences, that make up like paragraphs, and so on and so forth. Um, and there are meanings embedded in the language that we speak, and one way to know that is like when I speak, you kind of understand. So we know that like whatever is in these words have some meaning attached that like you and I somewhat understand, right? Like so, there's a way that we communicate, and so to say, like about these words. So these words have something mysterious in them. So I guess the premise of like large language models and AI in like natural language processing is like, can we build an AI system that understands that semantic context, which is like the meaning context behind these words that we speak, and use that to to teach a machine how to speak like us, think like us. Think like us, or write like us, right? Like so, and that this explanation may be kind of jumping the gun, but like back to tokenization. So machines need to understand, or like need a way to interpret words, right? But they can't see words, right? So we do this interesting thing called like tokenization, whereby we convert every word that we have in our vocabulary. I mean, it depends on like the kind of like the tokenization, or like the algorithm you use to make the tokens from your vocabulary. But broadly speaking, you can think of this as like words in your vocabulary, right? Like for example, if I have a vocabulary that only consisted of like 4 or 5 words, then tokenization is the process that maps those particular words to like integers, right? And then the embedding layer transforms those integers that are mapped from the tokens, and here you can consider tokens as words, but like embedding layer is a mapping between the token space, the token IDs to some kind of vector space, right? Like so, and that's what the embedding layer does. So now let me try to solve a little bit of like the positional encoding. All right, let's see. All right, let's see. Let's try to read the theory first. Transformers process all tokens in parallel, so unlike recurrent neural networks, RNN stands for recurrent neural networks. They have no built-in notion of token order, sinusoidal positional encoding, and solve this by adding a fixed deterministic signal in each token embedding that encodes its position in the sequence. The encoding uses sine and cosine functions at different frequencies, producing a unique positional fingerprint for every position. The output is a matrix of shape, sequence length, and D model, dimension of the model, with all values in -1 to 1. And it's a closed set. What it is, sinusoidal positional encoding is a fixed signal added element-wise to token embeddings before they enter the transformer encoder or decoder stack. It requires no learned parameters for a given position and dimension. The encoding value is computed by evaluating a sine or a cosine function at a specific frequency. Each position gets a unique vector in the real space of D model, computed once from a deterministic formula given a token embedding. Yep. All right. At position pos, the input to the, so this is the formula that we have, which is, let's see, converting it into, and the input to the transformer is where positional encoding, like input to the given a pos is, so this like, oh my goodness. Circled. Like, let's see, is return embedding of the position plus positional encoding of the position, where pos means pos is equal to, yeah, pos is the position. All right, where PE pos is, where is the sum? All right, let's see. Key encoding 4. Write it down. Input add position is equals to embedding. And I is the dimension pair index ranging from 0 to d model divided by 2 minus 1, and d model is the model dimension. Even index dimension 0 to use sine, odd index dimension use cos, right? Okay. The shared argument for each. All right. Yeah. The shared argument for each sine. All right. So let's see. Define theta of I is equals to return. This is a vector, right? Oh. Okay. Let's see the frequency schedule. 10,000. Yep. Of 2I divided by d of model. All right, let's see if this works. Oh, okay, if it's sequence length of 4. Let's try to look at some examples. Consider a D model of 4, sequence length of 3. The output is a 3 by 4 matrix because it's matrix. The input matrix will be a real 2, 3 by 4. Dimensions pair I equals to 0 for column. Okay. And 0 for column 0, 1. Why is this the case? Okay, so they were column wise. That's interesting. Because what do I read again, right? There's a fixed signal added element wise to token embeddings before they enter the token encoder or decoder stack. It requires no learned parameters for a given position, and for a given position and dimension, the encoding value is computed by either sine or a cosine frequency at specific frequency. Each position gets a unique vector in real space of D model, dimensional model, computed once from a deterministic formula given a token embedding at position pos. I'm having a hard time understanding what the position pos means here. Is it an integer? So it doesn't seem like an integer. This is element-wise addition. So both vectors share the same dimensionality. The encoder adds zero learnable parameters is identical across all forward paths. Every match, every epoch, right? Let's see. Pos is the zero index sequence position. Yep. Yep. And every sequence means it is the row. And sequence here means the row, yeah. Sequence length. Is the dimension ranging from numeral. Okay. All right. Let's see. So the straightforward formula is to return. Let's see. Return. It's like if okay, let's see. Define specific encoding of seq length D model I if I is an even number, return let's see, np dot sign of, actually if I can use numpy, let's see, setup, placeholder, let's go to np dot zeros of what, D model. So basically what this is trying to do is something like num D model times, which matches R to the D model supposition, right? And then we want placeholder of I for I in for I yeah for I comma, it's deterministic so it doesn't matter. That makes sense. So let's see what I understood, right? So where we left off, we currently have something like this, which is E belongs to E is E is approximately, I'll just use this notation. E is something like sequence length into sequence length in and D model. I might be wrong here, but I'm trying to think through things. Where sequence length is the amount of distinct tokens slash embeddings we have in the input, and D model is the dimensions of embedding. Okay, currently have something like an individual embedding is E R to the D of model. So an individual embedding vector is a vector that belongs to the real space of D model dimensions. All right. Then we want a way to teach, want a way to let the model know that different orderings of the embedding matrix tensor that is fed into the encoder decoder stack. I want a way to let the model do it. Matter. Like, so we want to wait for the models to know that like different orderings of that, like sequence ordering of the tokens matter before they are fed in. And the way to do that is to inject some signal about the position the sequence slash embedding vector is in, right? So we want a way to say something like, we want a way to say something like, okay, this is the first, this is at position 0, this is at, I'm going to say something like this is at position 0. Excuse me. This is at position 1, and so on and so forth. Right, and the way that the attention paper proposed is to use something like positional encoding. The attention paper proposed that we use positional encoding, which uses sinusoidal functions to distinguish even and odd pairings, such that the angle that is supplemented depends on the angle that is supplemented depends on the I that you receive. The I that you receive, which is what? whatever the position is at that particular thing, and then 10,000 raised to the power of 2 to the I divided by d of model. All right, and given that we want even an odd pairings to always be kind of out of sync, I don't know. I don't understand the full reasoning behind this. I know that in the theory there was a brief discussion of this. I can revisit them once I get my thoughts out on this notebook. All right, so theta and the input that the input that is fed to the input that is fed to the encoder decoder stack will be something like the embedding at the position plus positional encoding at the pos, right? Where PE of pos will be positional dependent of like of either sine of either sine of what was it? Sine of theta so pos is pos, but like let's say I equals to sine of theta if I is divisible by 2, that means else it is a cos theta angle. I'm going to check if that is right. And that is right. And all right, I think that's about it. I mean, there might be a way to express this particular equation, conditional equation, in terms of like something like, I don't know, PE of cos I equals to there might be a way to express this in terms of like a real function of a complex function. I won't be able to do this off the top of my head right now, but I don't see why not, or at least my intuition tells me that you could probably express it like that. Let's see what we have. All right. So I think we basically have most of the things that we need. Let me just convert them to code, right? Online Python input numpy as and sure, why not? Okay, pass. All right. Print numpy dot. Let's see, numpy dot zeros all like 4 dimensions. What happens? Where's the NP? All right, yep. So I do get a an array of 4 zeros. Yep, that makes sense. And so on. All right, so let's see if I can do this. A equals to numpy dot zeros of 4, 5. A of I equals to 0 for I in the range of length of A and A. I feel like I can. It's been a while since I used NumPy, but I feel like there should be a way to say something like n by A equals to 1 if I is divisible by 2, else 0, else 0. Is there a way to do this? Let's see. Sure, yeah, not really. Yeah, let's do it the more tedious way, which is for I in range of length A, AI actually it's not right. Let me input array is equals to np dot zeros of sequence length by the model. Okay, let's see. For I in range of length of input array, and this should, let's say, sequence of length is 3, dimensional model is 4. There should be 0, 1, 2, print row number I j in print column number j. Yep, that makes sense. 0, 0. Yep, that makes sense. This should have been what, 0, 1, 2, and 3. So basically, this would be the pos, and this would be the I, right? And the easy way to do this, I know there's an easier way to do this using NumPy, but I can't for the life of me remember it now. I'll have to look at the documentation. So let's see, for I in range of length input array, for j in range if j is even even input array of ij is equal to np dot sine of theta of what's I is j and cos is I. It's funny. And d model is what? 4. Else input array of ij equals to np dot cos of theta of j, I, and 4. Let's see what happens. All right. I think this might be the simplest way to do it, or I mean, the most inefficient way to do it. Let's see. Let's see. When you turn the input array. Right, let's see. You just turn this off, and let's see. Print positional encoding of sequence length like 4, maybe 3, and 6. Let's see how it does that. Huh. Does this look right? You know what? Let's take it. So let's see. Let's run it and see what happens. All right, let's see. Output 010001. Okay, that looks right. 010000. Expected negative 0.989992. Got 0.9999. Let's look back at the theory. Why does it look different there? Oh. Also, why am I doing this? You know? Stupid in me. Let's see. Hopefully it works. Well, that didn't work. Okay, the first row is right. The second row is right. Is it right? No, it's not right. So that means our theta is wrong. Sometime right now. That's interesting. Okay. Yeah, this might be the problem. No, that was stupid of me. 10,000. That looks correct. Go to the even odd split. Applying sine to all dimensions or cosine to all dimensions can destroy the dimension's integrity. Well, the wrong exponent is shouldn't make a difference though. Wait a minute. Okay, let's see. So I'm not following that. Next columns. Okay, so this might be it, you know. is this? What I did. Okay, it's a theta issue. Let's see. Return np dot what's divided by define positional encoding to seek then the water is fundamentally the same thing, but still a two. Yeah. What the fuck? Constant set you raise the np dot range. All right, so this is right. It's not right. This seems to not be right. Probably not right. It's not right. Let's see what is wrong here. Hmm. Position 3 expected negative. Okay. Okay. Let me do this. Okay. So the angle is the same, which is cos divided by, all right, let's see, for position in range of sequence length, so that goes by rho, and within that you have for j in range of d model. If j, if j is an even number, np dot, so even number is 0, 1, 2, 0, 2. Sine or cosine cos divided by t. What the? Why is this just single I? And p dot sine of theta of I, but here the I is actually the j divided by d model, which is what I give, and position is just position. Okay, that's interesting. Let's take a close look at. I thought the theta value slash function. How we look at how the columns are paired in the transform. The sine and cos function are applied in pairs to the same underlying figures. If column j equals to 0 as sine and column j equals to 1 as cosine, what value of I should go into your formula for both of them to make sure they share the same? Uh, if column and column j is cosine, which value of I should go into your formula for both of them to make them share the exact same denominator? Why should they have the same exact denominator? Specification define each frequency denominator defines a unique 2D coordination plane. Column 0 and column 1 cosine from the first column to column 2 and column 3 from the second to the introduced. Now down. Take your time looking at how your loop indices J maps to those pairs 0 and 1, 2 and 3, etc. Alright, let's see. So what's happening here? Okay, position ij. I must be missing something incredibly simple here. I know that theta of cos I call number is equals to cos divided by 10,000 times 2I divided by d of model, right? Then the array of call number equal to sine of theta if call number even and cos of theta if call number is odd, right? Oh, I'm missing something here. like okay. Okay. So yeah. Yeah. Let me try to 0, 0 equals to sine 0, yeah, which makes sense of sine equals 0, 0 equals to 0, 1, 0, 0, 1 equals 0, 0, 1 equals 0, and that. Oh, I see. I see. It's probably t minus 1. It is funny how you can. Yes. I see. Man, I've said I see like too many times. Yeah. Think I am. Position 3, 2, 0, 1, 2, expected 0, 1, 2, 3 of 2, 0, 9, 9. 3 of 2, 0, 1, 2, 0, 3, 3. Yeah. I see. I see. Oh, some different. All right. Okay, for J is if that's interesting. Okay. Oh. Okay, that's interesting. There must be a way to do this. Okay, let's rubber duck this. Let me write the notes. Okay, theta I, but the thing to remember is that I value goes from I to d model divided by 2 minus 1, right? So the pairs that form will be 0, 1, 2, 3, so on and so forth. They should have the same angle, but phase shifted. So the same angle, but phase shifted. because of the use of the use of sine cosine. All right, let's double like this. Okay, you enter. Do we have a theta code? Do we have an initial theta value? Not really. We can start off with a pair number as 0, and then we instantiate the array that we are going to fill in. We go through the row number. For pos, this would be, let's say, 0. And then this will be what? 0. And if 0 is divisible by 2, which is 0, theta value for pair has to be theta divided by pair number, which will be 0. Yeah, that makes sense. And then position and the D model. So this is up to this point, it's correct. And then what will have to happen? Input array will have to be np dot sine theta value for pair. All right, that's makes sense. And then keep on going here. And then it goes to 1. All right, this is not divisible by 2, so it comes here and it checks. And up to this point, it has the same theta value, right? So then it goes pair number plus equals to 1, and then it goes back again, and this must be something like 2. All right, this is divisible by 2, so theta value for pair equals to pair number, but now pair number is 1, so this will be 1, position, D model, input position, model. Okay, so I cannot properly see why this might be breaking here. Let's go back to the head. Take a close look at where you reset or increment. Right now, your code loops through every single position row one by one. Inside each row, it loops through the columns and increments at every odd column. Pair number when the code finishes the very first row. Ah, okay. Right. You're right. My bad. Pair number. Let me set this here. Oof. Yeah. Let's see if I can. Don't give the answer, but what's a NumPy update? Thank you for the match. Must be incredibly stupid. Don't give the answer, but what's a NumPy? What's the match to the NumPy update to the code? Give me the maps so I can move in docs. Broadcasting. All right, let's say to multiply a column vector of position shape of sequence length of 1 by a row vector with paired column frequency shape 1 to D model divided by D model, or to generate the entire matrix of theta values in a single mathematical stroke. Um, okay, all right. How would you use numpy slicing and p dot? All right, let me see. So let's submit this to see if it works. Position vector is very simple. You create numpy range of sequence length by 1, right? I think that was one of the hints. All right. Okay, position vector 0, 1, 2. Alright, theta vector equals to np dot rank of 0 to D model divided by reshape 1. Yeah, but division vector equals to m dot r. Okay. Okay. Yeah, np dot r sequence length. Sequence shape minus control. Okay. Division divide. np dot exponent np dot store d model dot 2. Okay, that makes sense. Into minus np dot log of 10,000 divided by d log model. Yeah, yeah, these are why doing this is so good, because um, like I have a basic, you know, speaking understanding of the attention mechanism, or like the like attention is all you need paper, but I've never really like gone into the details to see what's how the sausage is made, and obviously you can see that I'm struggling with it. Um, and but it's a good practice for me. Um, it's always good to learn um, things that you don't know. I put a just embedded the zero sequence standard comma do model. Okay. Well, it's getting a bit late. Not a bit late, but a lot late. So I think I'll wrap it up here today. And um, as I said, right, like, yeah, such is life. Being having the privilege to do something like this in your free time is it's an amazing thing, and I truly feel it. All right, good night, or farewell to all the people who may watch it in the future, including me.